Deep beneath the ocean's surface, where light is but a memory and pressure is enough to crush everything, colossal ghosts glide in silence. Has life been pushed into a dead end of choices? Or does an unchanging physical framework silently shape all living things? From the fiery Cretaceous to the dark abyss of modern times, giganticization is no coincidence. Let's journey back in time to unravel why evolution created the same giant twice. At depths of approximately 3,300 feet below the surface, sunlight is almost completely absent, and the ocean transforms into a state difficult for humans to imagine. Temperatures hover around 39 degrees Fahrenheit, water pressure can exceed 1,500 pounds per square inch, and energy sources are virtually non-existent or unstable. Unlike shallow waters, where organisms can hunt frequently, here, an organism may have to wait days for access to food. In that environment, life does not thrive in a diverse way, but in an extreme way. Every characteristic must serve a single goal: conserving energy and prolonging life. It was under these conditions that two squid species, Architeuthis ducks and Mesonychoteuthis hamiltoni, evolved in a remarkably similar direction. However, upon closer inspection, their resemblance is only superficial. Their survival methods differ significantly. The giant squid can grow to over 30 feet in length, its body slender and elongated like a spearhead, while the giant squid is typically only about 20 to 23 feet long but much heavier, potentially exceeding 1,000 pounds. In other words, one is long and fast, the other is shorter but heavier and stronger. This difference is not accidental, but reflects two approaches to solving the same survival problem. To understand this, we need to go back about 100 million years, when their ancestors belonging to the Oegopsida group were still small, soft, and vulnerable organisms. In the deep sea environment, smaller individuals were at a clear disadvantage. They lost heat faster, consumed energy more quickly, and struggled to survive for long periods without food. Conversely, larger individuals could survive longer between infrequent hunting. Over time, natural selection pushed both evolutionary branches toward increased size, but the specific environment of each branch produced different results. In the vast temperate oceans, where space is open and prey moves quickly, Architeuthis ducks evolved to optimize speed. Its long, flexible body allows it to accelerate rapidly in short bursts, enough to reach prey before it can escape. Its long tentacles have suction cups with small teeth, creating a strong grip when it seizes a target. It can be envisioned as a swift, decisive predator, relying on precise timing to succeed. Conversely, in the cold waters near Antarctica, where temperatures are lower and energy is even scarcer, Mesonychoteuthis hamiltoni cannot sustain that strategy. Here, swimming fast means expending precious energy, so instead of becoming faster, it becomes heavier and stronger. Its thick body, well-developed muscles, and sharp, hook-like tentacles help it grip prey without chasing. If the giant squid is an active predator, the king squid is more like an ambush, waiting and seizing opportunities when prey comes within range. This difference is also evident in their body structure. Giant squid have suction cups with small rings of teeth, suitable for holding prey while moving quickly, while colossal squid have rotating hooks, providing stronger grip but less flexibility. One prioritizes control of movement. The other prioritizes locking down and finishing quickly. These are two completely different strategies, but both lead to the same result, becoming a giant creature. However, size brings both advantages and risks. As these two species grow larger, they also become more attractive targets for capable predators. In this case, it's Physeter macrocephalus, a whale that can grow to over 50 feet in length and dive to depths of thousands of feet to hunt. Sperm whales use echolocation to detect prey in the dark, an advantage that neither squid species can completely avoid. The circular scars on the sperm whale's body, thought to be caused by the giant squid's suction cups, suggest that confrontations between them are not uncommon. Remarkably, both squid species, despite differing strategies, face the same predator and the same pressures for survival. This leads to an evolutionary cycle where larger size helps them survive smaller threats better, but also makes them targets for larger predators. As a result, both evolutionary paths continue to be pushed in more extreme directions. The phenomenon of two unrelated species developing such similar characteristics is called convergent evolution. In this case, the common ground lies not in origin, but in environmental pressure. Both species face the same problem: how to survive in an environment with limited energy, high pressure, and low temperature. And although they start from two different paths, both arrive at a similar solution: increasing body size to optimize survival. In short, Architeuthis dux and Mesonychoteuthis hamiltoni are not alike because they share a close ancestry, but because they faced the same harsh conditions and were forced to adapt in the most efficient ways. One species chose speed, the other chose strength, but both reached the same ultimate result: becoming giant creatures of the deep sea. To understand why these explanations keep repeating, we need to go back in time, to an era when the ocean was far more brutal. Around 80 million years ago, during the Cretaceous period, the ocean was the domain of Mosasaurus, a marine reptile that could grow over 50 feet long and was almost perfectly engineered for hunting. Remarkably, Mosasaurus wasn't born this way, but rather the result of a transformation from a land-dwelling lizard. Upon returning to the aquatic environment, their foundations had to change to begin increasing drag and adapting, leading to the development of paddles, tails for propulsion, and elongated bases to reduce drag. More importantly, Their jaw structures became more flexible and powerful, allowing them to tackle previously inaccessible large objects. The arrival of Mosasaurus not only added another predator, but also completely changed the way of survival in the ocean. Before the time of Mosasaurus, one of the most successful groups of organisms was the Ammonite, mollusks with a hard spiral shell that acted as a natural armor. For tens of millions of years, this strategy was nearly perfect, because most predators could not penetrate that protection. However, when faced with a predator with a powerful bite and direct attack tactics, the hard shell gradually became a weakness rather than an advantage. It limited their mobility and reaction time, making it difficult for the Ammonite to adapt to changing environments. This is a prime example of how an evolutionary strategy can become obsolete, not because it was ineffective, but because surrounding conditions changed too rapidly. While the Ammonite continued to rely on defense, another branch of organisms chose the complete opposite path, abandoning protection in exchange for flexibility. This is where Tusoteuthis longa came in, an ancient squid that could reach lengths of about 30 to 35 feet. Lacking a shell, Tusoteuthis relied on its soft body and rapid movement to avoid danger, and used its long tentacles to effectively capture prey. This represented a shift from a survival strategy to an evasive one. However, despite its similar appearance, Tusoteuthis was not an ancient version of modern squid species like Architeuthis dux or Mesonychoteuthis hamiltoni. It existed in a completely different environment, where light was still present and predatory pressure was high, while modern squid mainly live in the deep sea, where energy is the deciding factor. Approximately 66 million years ago, a mass extinction event wiped out both Ammonite and Mosasaurus, depriving the oceans of once dominant species. This disappearance was not just an end, but a reconstruction, creating a new environment with different conditions. Shellfish began expanding into the deeper layers of the ocean, where competition was less intense, but energy demands were harsher. Here, the pressure to survive no longer came from immediate predation, but from the ability to endure for extended periods without food. This allowed the organism to survive more stably in the cold, resource-scarce environment. Therefore, the ocean once again created giant creatures. But this time, not to cope with predators in shallow waters, but to adapt to the harshness of darkness and scarcity. Looking back at this entire journey, it can be seen that evolution is not an infinite creative process, but is limited by the environment and the laws of physics. Furthermore, evolution is often described as an endless process of variation, but in reality, it is tightly bound by the laws of physics. This raises a crucial question. If evolution can produce countless forms, Why do we constantly observe similar forms appearing in completely unrelated species? The answer becomes clearer when we consider life in the ocean, where movement, energy, and survival are governed by strict physical limits. A striking example can be found in the comparison between Ichthyosaur and Delphinus delphis. Ichthyosaurs lived over 90 million years ago and could reach lengths of 10 to 30 feet, while modern dolphins typically range from 6 to 8 feet in length and can swim at speeds of up to 35 miles per hour. Despite this difference in time and lineage, both share a nearly identical body plan. A streamlined, torpedo-shaped form, a powerful tail used for propulsion, and fins positioned to maintain stability. This similarity is not accidental. It is the result of a fundamental constraint: drag in water. Water is approximately 800 times denser than air, meaning that any inefficiency in shape dramatically increases resistance. Studies in fluid dynamics show that streamlined bodies can reduce drag by up to 50% compared to irregular shapes, allowing organisms to conserve energy while maintaining speed. For a predator that must chase prey or escape being hunted, this difference is not minor. It is the difference between survival and death. Both ichthyosaurs and dolphins face the same problem: how to move efficiently through a dense medium while minimizing energy loss. A bulky or uneven body would require significantly more energy to maintain speed, making it unsustainable in the long term. Over millions of years, natural selection eliminated inefficient forms, leaving only those that approached an optimal design. As a result, both species converged on the same streamlined structure, not because they were related, but because the environment allowed very few viable alternatives. This principle extends beyond movement into energy management. Marine predators must balance energy intake with expenditure. A high-speed chase, for example, consumes a large amount of energy in a short time. If the body is not optimized, the energy cost of movement may exceed the energy gained from food, leading to eventual failure. By reducing drag and improving propulsion efficiency, both ichthyosaurs and dolphins could maximize their chances of successful hunting while minimizing wasted energy. The convergence between these two species demonstrates a broader rule. Evolution is not an unlimited creative force, but a process shaped by constraints. When different organisms face the same environmental challenges, whether it is water resistance, energy efficiency, or movement stability, they are often pushed toward the same solutions. If this has changed your perspective on evolution, Keep following and subscribe to the channel because the next story will delve even deeper into the recurring laws of nature.